Welcome to another episode of Mustang Physics Screencasts. Today we're talking about comparison problems and how to solve them. First, a lot of words on this slide. Let's just read through it, make sure we understand what's going on here. All right, a comparison problem. What is it? It's a problem where you've got the motion of at least two objects, and so you have to stay organized in these kinds of problems. One of the things we'd recommend that you do is draw a diagram of the motion of each object separately. Now, there's usually somewhere in the problem something that identifies a relationship between the motion of one object and the motion of the other object. Find that link, because it's not uncommon that you have enough information available about one of the object's motion to solve for what's going on with it, but you need that to be able to solve for something about the motion of the other object. Now, if you need to, then find information about the motion of that first object in order to then find new information about the motion of the other object. Now, foremost among everything, you got to identify what the question is asking. If you don't know what you're trying to solve for, you can get super lost in these problems. So finally, one more tip from this slide, and that is that it can be useful sometimes to think about the steps you need to solve the problem from what you know, but other times it might be more useful to kind of work backwards from what you were trying to find back towards what you know. Guys, every comparison problem is unique. You really just got to use logic and reason and what you know about kinematics to figure out each one. So follow all the rules of kinematics and kinematics problem solving as you're solving the problem, just keeping in mind what's going on. Now let's take a look at a reasonably complicated comparison problem on the next slide. I'm going to go full view on this so we can read it a little bit better. All right, so we've got two ice hockey players. They make a bet. One's going to shoot the puck with only one hand, and he's going to use his non-dominant hand. So if he's a righty, he's using his left hand. The puck's going to travel 178 feet from one goal to the other, and it's going to do it at a constant speed. The other player thinks he can skate that distance and beat the puck. The skating player, the skater, starts from rest at the moment the puck is shot. So we know they start at the same time. Now the skater gains speed at a rate of 14.1 feet per second over the first 55 feet until he reaches his maximum velocity, which he maintains the rest of the way. The skater wins. When he crosses the goal line, the puck is 6.5 feet behind him. How fast did the puck travel? Well, I'm going to go dual screen here. The reason I'm going dual screen is because I want to remember what it was that we should be doing as we do these problems. All the stuff that was on the left side here, and then do that on the right, starting with draw a diagram of what's going on. So as we draw that diagram, well, we're going to have a diagram for the puck, but we also have to have a diagram for the skater. Now the puck ends up traveling not 178 feet. Remember it said that it was 6.5 feet behind when the skater finished? It was supposed to go 178 feet. In fact, it does, but we're trying to figure out how fast the puck traveled. To do that, we're going to have to use the distance that it moved during the same amount of time that the skater took. Because we know that the puck had moved 178 feet minus 6.5 feet at the moment that the skater finished, and we know that the time for the puck is equal to the time for the skater, because they started at the same time, and we know where the puck was when the skater finished. Now, we can see right now, since we've got the distance the puck traveled, 178 feet minus 6.5 feet is 171.5 feet. And we want to know the speed of the puck. Remember that the puck is going to travel at a constant speed. We only have one equation to find then. How fast does the puck travel is going to be V average equals D over T. Well, at this point, what we need to find then is how long did it take the skater to finish, because it's implied in the problem that the skater and the puck took the same amount of time. When the puck was 6.5 feet behind the skater, it's the same moment as the skater finished. and the skater started skating when the puck was shot. So their beginning and end times are the same to that distance. So that means we shift our attention over to the skater. So taking a look again at the skater and his motion, remember what we're really trying to do right now is still just draw a diagram of the motion of the object, but as a part of doing that, we already identified the information that relates one motion of the object to the other. They have the same times. We've also identified what the question is asking and what we'll need to determine. We now have figured out that what we're looking for is the average speed of the puck, and we need the time of the skater so that we know then the time of the puck. So let's work on the skater, and at this point I think we can go full screen again and go back over to that diagram. Let's re-examine what's going on with the skater. So he starts from rest. VI is 0. He gains speed. That means he's accelerating, and here is that rate, feet per second is an acceleration. But he only does that for 55 feet, even though the whole course is 178 feet. By the way, that is the right distance from goal to goal on an NHL rink. Now, at that moment, he reaches his max velocity, which he maintains the rest of the way, which means whatever his final speed was for the first chunk of motion, that's his V average the rest of the way. So let's scroll down and draw a diagram of that motion. For the skater, we know that the skater there he is. He's skating along, VI is 0. He's going to skate 55 of the 178 feet. And at that moment, we break the problem up into a new interval, because whatever his final speed is as fast as he can go. That's the average for the rest of the way. Now, the rest of the way would be the 178 feet total minus the 55. So the rest of the way is 123 feet. Now we know one more thing as he's skating, and that is his acceleration at the start. That acceleration is 14.1 feet per second. What that means is that during that interval, we have got 3 chunks of information. We've got how far he travels, 55 feet. We've got the initial velocity, 0, and we've got the acceleration, 14.1 feet per second. What that allows us to do is solve for 2 things. One that's really important, we've got to solve for the time in this first interval. Eventually, we're going to have to solve for the time in the second interval, and we can add that up to get the total time that it took him to go the 178 feet, which is our goal, since in order to find the speed of the puck, we need to know how long it took the skater to finish, because that's how long it took the puck to go 171.5 feet. Going back to the skater. The other thing we're going to have to solve for in the first interval is what's the final velocity? Because if we can solve for the final velocity, we then know the average speed during the second interval, which we can use with the distance during the second interval to solve for the time in the second interval. So now let's just go about doing it. So let's work on the first interval first. So in that first interval, we know that the time can be found with the square root of 2d over a, because VI is 0. That would be the square root of 2 times 55 feet over 14.1 meters per second. When we calculate that out, we get a time of 2.79 seconds. We'll go ahead and put that right back into our diagram, but I'm going to color code it so that I know it's something I calculated. Now, in order to calculate the final speed, I can again go back to the original data that I had I've got VIA and the distance, so final speed is the square root of 2 times the acceleration times the distance. No plus minus issues here because he's moving in the positive direction, so his displacement is positive and his acceleration is positive. So that's the square root of 2 times 14.1 foot per second times 55 feet. Notice what happens. Feet times feet, this one and this one, they square. So we've got feet squared per second squared, which is weird, but don't forget we're going to take the square root, so we end up with a speed in feet per second. So 2 times 14.1 times 55, square rooted, don't forget to do that, gives us a speed of 39.38 feet per second. Now that is the final speed at the end of his acceleration, 39.38 ... feet per second, but it's also V average the rest of the way, since the problem told us that he maintains that speed the rest of the way along to the end of the 178 total feet. What that means is we can now solve for the time in the second interval. The time in the second interval, because he's keeping constant speed, would just be d over V average. Now, because we're looking for just the time in the second interval, we're going to use just the distance in the second interval, 123 feet, and just the V average during that second interval, 39.38 ... feet per second. Use the unrounded number. When you do that, you end up with 3.12 ... seconds. Now, those two times, 2.79 seconds for the first interval and 3.12 seconds for the second interval, they can be added together to get the total time, because of course time is a cumulative thing. If you spend a little bit of time doing one thing, a little bit more time doing something else, that time just adds on to find the total. So the total time for the skater would just be the time it took him to accelerate in interval 1 plus the time it took him to keep his speed in interval 2. That's that 3.12 seconds plus the 2.79. So we end up with a total time of 5.9 ... seconds. Now we're done with the skater and everything we have to find. There's more we could find, but we don't need to, because we can now go back to the puck. We had already reasoned through that the puck and the skater began at the same time, and at the moment the skater crossed the finish line, which we have now figured out was 5.9 seconds later, that the puck was 6.5 feet behind him, which means the puck had gone 171.5 feet. So in order to figure out how fast the puck is going, well, heck, we can now do it. The puck has an average speed, and we can find it with d over t. The puck ended up going 171.5 feet in 5.9 ... seconds. When we calculate that, we get that the puck was going about 29 meters per second. Excuse me, feet per second. Aha, voila. You can see if we back way off now and look at the entire page, but there's a lot of writing on the page. To look at this afterwards doesn't make a whole lot of sense unless you use diagrams, subscripts, and labels to make sure that you understand what's going on. So notice how I've divided my page. Everything above the red line that I just drew is for the puck. Everything below it is for the skater. Instead of saying t equals t, I'm saying the time for the puck to travel is equal for the time the skater to travel. I've labeled one interval and another, and even kept the calculations that were about the first interval near the first interval, and calculations that are about the second interval of the skater's motion near the second interval. The more you can organize your work, the more you can use logic and reason to just work your way through the problem and eventually get to your goal. Don't be surprised if you end up solving for some things that you didn't need along the way. Be patient with yourself. It's going to take some practice with comparison problems before you get more efficient with solving them. All right, hopefully that's a good introduction to what kinds of things you need to do to solve interval problems. Stay organized. Keep track of what information means what. Draw that diagram so that you can keep a really good handle on what the motion actually looks like. And always keep your eyes on the prize. Try and make sure you understand what it is you're trying to solve for so that you can reason through with what you have how you can get a little bit closer to the goal with each calculation and each piece of logic. Good luck.